Okay, welcome to another video on apply electricity. This is Dr. Osman Al Hassan, your apply electricity lecturer. So today I'm going to be solving the first semester examination. The past paper we started solving yesterday, so I'm going to continue from that question number that we stopped. If you can remember, we stopped at question 30. We solved question 1 to 30, right? So I'm going to continue from question 31 to question 60. So I'll be solving 30 questions today. Okay, so let's continue from where we stopped. Okay, and this is a solution for apply electricity first semester examination 2022-2023 academic year, right? So let's continue from question 31. Okay. Question 31. I have question 31. Half a circle is called, right? Half a cycle is called A. We have a period. B. A cycle. C. An alternation. D. A frequency. So when we talk about half a cycle, we know that if you have, for example, a sine wave, right? Let me use a different color. You know that if you are having a sine wave, for example, let's say we have here to be 2 pi, and then here is pi. So for a complete cycle, okay, this part is not good. No, this part is always bad for me. Let's say we get something of this nature. Okay, so this is a complete cycle, right? Complete one. So we have one cycle here. Okay. Now, with this kind of cycle that we have, you can see that half of this, right? For example, half of this, we call this alternation, right? Alternation. Alternation. That's why we define an alternating current as what? As a waveform that changes between what? Positive and negative, meaning that alternate, right? Meaning it's changing. So half of a cycle is called an alternation. So the answer here is going to be C. Okay. Now let's go to question 32. A sine wave of 2000 Hz, right? Question 2 here. This was question 1. So meaning we have frequency is giving us 2000 Hz, right? 2000 Hz. We'll go through 20,000 cycles in that seconds. So meaning here you can see that here we are giving the number of cycles. The number of cycles here is giving us 20,000. So we have 20,000 for this. Now you can see that we are asked to find the circles, right? Meaning time. So if you are given 2000 hertz and then the number of cycles is 20,000, you should find the time. Okay, that's what this is just about. We know that frequency is going to be equal to number of cycles over time. So with this, if you look at what we are giving frequency, we are also giving cycle. So we make time the subject. So time here is going to be equals to frequency over, let's say, n, whereby n here is just representing the number of cycles. So this becomes frequency, time here is going to be equals to, rather, frequency f. We are making time the subject, so you multiply both sides by time, then you divide by frequency, so you get number of cycles over frequency. So time here is going to be equals to number of cycles, which is giving us 20,000 divided by 2,000, right? So this will just give us this one to give us 10. So we get 10 seconds, right? So this question, we are going to get the answer to be what? 10 seconds. So here the answer is what? D. Okay, we get here the answer for question 32 to be D. Now moving forward, we have question 33. We have question 33 here. If the root mean square value of a sine wave is 20 volts, the peak value is approximately, so here we are giving the root mean square value. So, and this is voltage, meaning root mean square voltage here is giving us 20 volts. The peak value is approximately, peak value, which is the peak voltage, is the same as what? The maximum voltage. So we know that the root mean square voltage is going to be equals to 0.707 times what? Maximum voltage, which is the same as 0.707 times peak voltage. So we make peak voltage the subject, we just get root mean square value, which is the voltage here, over 0.707. So with this, we are going to do the division here. So here we are giving this. Okay, so we know from the question the root mean square value is 20 all over 0.707. 20 divided by 0.707. So I get 28, right? 28.28 volts. So when we check here, the answer, we have 28, right? So the answer here, we get 28. Now, let's go to the next question, which is question 34. Question 34. What is the peak voltage of the sine wave below? So we are given this sine wave here. Okay, let me enlarge it. So we are given this sine wave. Okay, and we asked to find the peak voltage, which is the same as the maximum voltage. So when you look at the sine wave, you can see that we have a maximum voltage, and we have here to be 10. But when you look well, you can see we have 6 volts, right? The sine wave didn't start from 0, right? I mean, on on the y-axis, which is the voltage, it's not starting from 0, it's starting from 6. But we are interested in the peak voltage, mean the rise in voltage, right? Respect to the reference, right? So we have this reference starting from 6 volts here. So when it comes to getting the peak voltage here, which is the same as the maximum voltage, here we can just take 10 here minus 6, right? So we have 10 minus 6, so that will give us 4 volts. So the answer here will be 4? Okay, because here the reference is 6 volts, not 0, as we always see. Now, active power is measured in watts. Okay, watts. So the answer here is A. VA is for apparent power. Okay, VA. Question 36. So let me reduce this so that we get back to normal size. Okay. Now, question 36. The electrostatic force is also known as, if you look at, we have A, charge force, B, electron force, C, Coulomb's force, and then D, none of the options. So the answer here is going to be C, Coulomb's force, right? Because when it comes to electrostatic force, meaning we are talking about the force between charges, right? Let's say I have charge 1 and then charge 2, right? We want to find the force, right? That's what we refer to as the electrostatic, which is the same as Coulomb's force, because it's Coulomb's law that gives us the force, right? So we have question 36. The answer is C. Now let's move to question 37. Coulomb's law is given by the expression. Okay, so we have Coulomb's law is given by the expression. We know, like I just indicated earlier. Okay, let me refer to this. Let me use small letters for the charge. I have charge 1 here and charge 2. Right? To find the force, you know the force is going to be equals to, or we can say the Coulomb's law states that the force between two charges will be directly proportional to the product of the two charges, and inversely proportional to the square of the distance between the charges. So let's say the distance here is D. So we get this formula. This implies the force, you bring the constant K here to be Q1 Q2 over D squared. So when we check here, the answer here will be B, right? B here. Question 38. In Coulomb's law, epsilon is known as, so Coulomb's law, when we have this, right? Let me even expand on this. So with this, the constant K here is actually the same as 1/4 pi epsilon, right? So when you replace this in the formula, you get Q1 times Q2 over what? 4 pi epsilon d square. And this epsilon is called, we refer to this as what? Absolute permittivity. So here, the answer here is going to be what? B, absolute permittivity. So in the letter. Now, question 39. The force between two charges is 120 newtons. If the distance between them is doubled, the force will be, here we are to find the force. Okay, that is question 39. So question 39. From what the formula I just wrote earlier, you can see that force, right? Because here we are talking about two charges, so it's the same formula. You can see the force here is what? Inversely proportional to the what? The distance between the what? The charges, right? Distance between the charges. So when it comes to this question, you can actually solve this in quite a number of ways, right? There are several ways you can think about it, this question, but one of the easiest way, okay, though it's actually the hardest way if to understand, is that we can just write this formula here, which is force is inversely proportional to the square of the distance between the two charges. So that means that if I increase the force, right? Let's say force here is what? Increase, right? If the, the other way around. Let me do it the other way around. If you were to increase the distance between the what? The charges rather, you can see here the force is going to be what? Reduced, right? So the force will be reduced. And then the other way around, right? Let's say you increase the force, and then meaning the distance between the two charges is also going to what? Decrease. Right? So to solve for this, what you can do is that we can say that if you are given a force, right? Let's say in this case we are given 120 newtons of force. Now when it comes to the distance, right? The distance for this, for the first case, right? The force between two charges is 120. So this is the first case, right? So I have 120, and then we don't know the distance yet, right? And then we just know that we are giving it give us 120. So the second part of the question, which is if the distance between them is double. Now the second scenario is, now let's say this corresponds to a distance d, right? Now let's say in the second case, this distance we now double the distance d here, right? Meaning that will be, let's say, twice of the distance d, which is 2d. You can see that by doing this, the question now becomes what is going to be the force, right? So by looking at the relation between the force and the distance between the charges, we can say that because here we are dealing with the distance square here, right? And then once I'm increased the distance from this, the force will reduce. But we don't know by how much is going to reduce. So what we are going to do that here is what? Square, right? So we are going to make this one to square. The doubling of the distance is also going to be square. That will give us 4d square. So what this simply means is that by doubling the distance between the plates, right, the charges in this case, what that means is that the force here is going to reduce, but it's going to be reduced by what? Here's what? 4. So you can just take 120 divided by 4, and that will give us 30 newtons, right? So that will give us C. That's one way of thinking about, which is the easiest way. The other way, which is that we can look at the formula I wrote here, which is that the force is inversely proportional to the distance between square of the distance between the two charges. So we can expand on this to mean, which implies that, let's say, force will be equal to, let's say, K, which is a constant, because we are bringing constants over what? D square here. This is just capital K1, right? I'm just replacing by just, let's say, a constant. So once I've done this, right, this is for F1 in that case. So the first case whereby I have V1, meaning F1 rather, equals to 120, meaning it's actually equals to 1 K1 here over what? D1 squared. Okay? Let me also need to be D1 squared. Now the second case whereby the distance is being doubled, right? That means I'm going to get what? Let's say K2 here. But remember, the constant K here is going to be the same for both cases, right? So here I'm going to still maintain my K, because that's just constant. That constant is the same for both cases, for both forces. So I can write K1 will be equals to K1 over D2 squared. But remember, D2 here is actually going to be equals to what? Twice the what? D1, because it's D1 is being doubled. So when we replace this, we get here to be 2D1 squared. So we get F2 here to be equals to K1 over 4 D1 squared. So by looking at this now, you can actually see clearly that I can write, this is F2, which is the second force will be equals to K1 over 4 D1 squared, which is going to be equals to, remember now, K1 over D1 squared is the same as what? It's going to be the same as F1. So I can write F1 here over what? 4. Okay. Once we've done this, you can see now we are just going to get 120 F1, which is 120 over 4. That will give us again 30 Newton. So that's second way of thinking about this. Now let's go to the one, question 40. The electric field intensity at a point situated 4 meters from a point charge is 200 newtons per coulomb. If the distance is reduced by 2 meters, find the intensity. Find the field intensity. The field intensity will be what? Will be. So the electric field intensity at a point situated 4 meters from a point charge is 200 newtons per coulombs. If the distance is reduced by 2 meters, the field intensity will be. So you have to find the field intensity. So this question is similar to question 39, right? Here we are now talking about electric field intensity, and we know that electric field intensity is the one, the force exerted on what? A positive test charge, which means 1 coulomb of charge. So you can even see that is even stated here, right? The distance between the 1 coulomb of charge, which is a point charge, that's what that means, right? Is 4 meters. So we can write the formula for electric field intensity, which is the force exerted on 1 coulomb of charge. That means we get here to be the charge. Let me use small letter so that there will be consistency, right? Over d squared here. Then I have K. So this is the formula for what? Electric field intensity, right? Now you can see it's similar to the case of the force. So you can see here too, we can just simplify to mean what? The electric field intensity here is inversely proportional to square of the distance between the what? The two charges, right? Right. One is a test charge, which is 1 coulomb, and the other charge. Now we can use the same case here, right? But this time you can see that we are giving the electric, we are giving the distance here to this time to be 4, right? The distance is 4, and then that is for the first distance. Okay, first distance here is 4 meters, and then the second one is now reduced to 2 meters. Okay, so in this case here, what we can do is that we can see that this one is being doubled, right? Twice. So the difference between the D1 and D2 here is what? 2 meters. All right. So again, I can use the first case that I use, the first method, right? If here we are giving the electric field intensity is 200 newtons per coulomb, right? That corresponds to 4 meters. Now we have to find if this is reduced to what? 2 meters, meaning you just reduce this, right? Just reduce this by 2. Okay. Again, by looking at this formula here, you can see that if I increase the distance, right, this thing will reduce, right? The electric field intensity will reduce. So likewise here, if you reduce the distance, right, that means that what? The electric field intensity will increase. So meaning you can see here there's reduction, right? And that reduction here is reduced by what? 2, right? Meaning you reduce it by 2. So I can take that difference, which is 2 here, 2 meters. And then again, we make use of this because here is d squared. I can square the what? The 2, so that we get here to be 4, right? Now that means that since the electric field intensity is going to what? Increase because I'm reducing here, I'll just multiply the what? 200 by what? You know it's going to be increased, so by 4. That is going to give me 800 newtons per coulomb. So we get here the answer to be what? B. Okay, to be B. Now we have B here. So we have B. Now we go to question 41. The direction of electric field due to a positive charge is. So the direction of electric field when you have a charge, for example, if you have a positive charge, right, the electric flux, right, they tend to what, diverge from the charge, right, the point. Let's say you're having a point charge, so you can see this here, the arrows here, they are indicating the direction of what, the electric field, because within this, the electric flux here will give us what, electric field strength, or you can say the electric field. Here we have electric field, we get electric field. So you can see the direction here is just indicating the direction of what, the electric flux. So here you can see the direction, they are what, moving away from the what, the charge. So that means when you come here, it's actually going to be A. For a positive charge, the electric field due to a positive charge there is away from what, the charge. Now question 42. A capacitor stores 0.24 coulombs at 10 volts. Its capacitance is, here we are given the charge, and then the voltage, and you are asked to find the what, the capacitance. So you have to use this formula, right, which is charge is going to equal the capacitance times voltage. Or you can start by just saying that charge, we know, is going to be that proportional to voltage, and then you bring your equal sign, and then that constant, which we term as what, the capacitance C. So you make C the subject, that will be charge over voltage. The charge here, which is given as 0.24, and the voltage is 10. Okay, so with this we are going to get that will be 0.024 farad, right? The units for capacitance is farad F. So when we come down here, it's going to be equal to what, A. Our answer is A. Question 43. The unit of capacitance is, so when you come to the units, if you can't remember the unit, you can just come and look at this same formula that I wrote here, which is capacitance will be equal to charge, and the unit of charge is what, coulombs, right? Coulombs. And then voltage, the unit is volts, right? So you can see that we are coulombs per what, volt. So the answer here is going to be question what, C. Okay, now moving to question 44. If three 15 microfarad capacitors are connected in series, the net capacitance is, here we are giving 3 capacitors, right? We are giving 3 capacitors, and then each one is 15 microfarad. So that means I have 3, and they are connected in series, so meaning I have 1, 2, 3. So here is 15 microfarad. Here is also 15 microfarad, and then here is 15 microfarad. So we have 3 of this. You connect them in series like here. So you have to find the net capacitance. So net here, capacitance meaning refers to what? The equivalent capacitance, right? Which is going to be equals to. Now, the simplest way to get this is to make use of what? The fact that since we are dealing with 3 capacitors and they have the same capacitance, right? Meaning they are identical. So if they are identical, we know that the capacitance formula in general is going to be equal to, let me write the general formula for capacitance connected in series. It's actually is the same formula as what? Similar to the formula for resistors connected in parallel. So the 1 over equivalent capacitance will be equals to, since I'm having 3, meaning 1 over C1 plus 1 over C2 plus 1 over what? C3. So we have this formula, right? Now with this, you can reduce this further. If C1 and C2, they are all the same, right? The shortest way is to just say that in that case, you take the capacitance over the number of what? Of capacitors, right? So since they are identical, meaning C1 is equals to C2, which is equals to C3. If you don't want to do that, you can just replace C1. They are all 15 microfarad, right? Then you get the same answer. But the easiest one will just take the capacitance, which is 15 micro, over the number of capacitors, which is what? We are dealing with 3 of them. 1, 2, 3. So divided by 3. And that is going to give us what? 45. Let me see. No, not 45. We are dividing by 3. Question 15. Let me look at this well. Yeah, that will be 15. Yeah, 15 divided by 3. Sorry, you will not get 4. It's 5 rather. I don't know what is wrong with me. It's supposed to be what? 15. 15 divided by 3, that will be 5 microfarad. So the answer here will be what? A. Now question 45. If the 3 capacitors are connected in parallel, the net capacitance is, here there is a mistake with this question, right? So here, in order to make sure that the answer is inside, right, question, the possible answers there. So I'll make here, if there what, if you have what, 10. So if you have 10 microfarad, if you have 10 microfarad capacitor, okay, not that way. Okay. Let me bring the 10 here. It should be, if you have 3 10 microfarad capacitors, microcapacitors, and they are connected in parallel. So meaning now I'm having 10. We have 3 of this, and each one is 10 microfarad. 10 microfarad here, and this one too is 10 microfarad. And this time they are connected in parallel, which is this, right? Meaning end to end. So with this, the capacitance, equivalent capacitance, again here, since they are connected in parallel, is going to what? C1 plus C2 plus what? C3, right? So that would just give me 30, right? That would be 10 plus 10. Remember, it's 10 micro. Okay. Let me write this. So I have here to be equivalent capacitance will be 10 micro plus 10 micro plus 10 micro, right? So that will give us 30 microfarad. Or we can use this one question, this simple formula here. Since they are, each of them is 10 microfarad, that means they are identical. So we can use N times what? C. right? And here is the number of what capacitors, and there are 3 of them, so meaning 3 times the capacitance, and the capacitance is 10 microfarad, so times 10 micro, so that will again give us 30 microfarad. So the answer here is 30. Question 46. A dielectric material must be, when you are talking about dielectric, it must be what? A, resistor, B, good conductor, C, an insulator, and then D, a semiconductor. So the answer here is what? C. When we talk about a dielectric material, it's actually the insulating material you place between 2 parallel plates, right? 2 parallel plates. That's what we refer to as a dielectric material. So you see, the capacitance of a capacitor is not affected by A, distance between the plates. So let me write here. Let's say you have a capacitor. The symbol for capacitor is actually this, but this comes from the having 2 parallel plates, simplification of 2 parallel plates. So let's say I have a plate here, right? Another one is here. So we have 2 of this. Let me make here, for example, we have this. These are 2 plates. So the distance between the 2 plates that I have, this distance is what? D. So that's the distance. So if I'm having the 2 parallel plate, which is a capacitor, the capacitance of it is going to be equals to the absolute permeability, right, times area over the distance between the plates. So you can see here the area, when it comes to designing the capacitor, the area of the plates, right, meaning the plates here, this is the area. It depends on the area, then the distance between the plates, and then the absolute permeability of permittivity of the material. Right? So with this, when you look here, the first one, a distance between the plate, that means it's true. C, area of the plates, which is true. Then B, the thickness of the plate, which is wrong, right? Which is wrong. Don't confuse here the thickness of the plate here. We sometimes refer to the distance between the plate to be what? The thickness of what? To be the thickness of the dielectric material. So D here, we refer to it as what? The thickness of the dielectric material. That is different from what? Here, the thickness of the plates, right? So don't be confused about it. So the answer here is B. So that's the one that is not affected by the capacitor, is not affected by the thickness of the plate. Question 48. Voltage applied across a ceramic dielectric produces an electrolytic field 100 times greater than air. What is the value of the dielectric constant? Dielectric constant means the relative permittivity of the material, all right, of the dielectric material that you have. And that's why I refer to as what? Relative permittivity, because we look at that permittivity relative to that of what? Air, right? That of air. The permittivity of the mirror relative to that of air. So the dielectric constant is the same as the relative permittivity. So if here you can see we have 100 times greater than air. So that's just giving us the value for the dielectric constant. So the dielectric constant is going to be 100. So the answer here is C. Question 49. 3 capacitors each of capacity C is connected such that the resultant capacity is 2/3 of what? The capacitance, right? Meaning C here, which represent the capacitance. What is the arrangement of what the capacitors in the circuit? Here, I think this question is the hardest question in this in all the questions that I've solved earlier. It's not that hard, but it's just that it's tricky, right? I would say it's the trickiest question. Why am I saying it's the trickiest question? Because here we are given 3 capacitors. Each is having a capacitance of what? C, right? That's the value of the capacitance. We are using C here to represent the value of the capacitance of each capacitor. So there are 3 of them. So meaning I have 3 capacitors, one here, C, another one, the same capacitance, C, another one, same capacitance, C. So these are 3 of them. So you can see that they are identical, meaning they have the same capacitance. Just like identical twins, they tend to have the same age, right? The same thing here. When you have capacitors that have the same capacitance, we say they are identical. Now, to go about this question, we are interested in how they are being arranged so that they will give you what? The resultant capacity, meaning the equivalent capacitance. Resultant capacity here refers to what? Referring to the equivalent capacitance, which is equals to 2/3 of what? C, meaning the capacitance. Now, we have to find how they are being connected to produce this equivalent capacitance. When it comes to capacitance, just like resistors, you can connect them what? In series, right? You can also connect them what? In parallel, right? And then you can even mix them up, right? Parallel connection. Some of the capacitors are connected in parallel and then in series with other. But let's start with what? The first 2 scenarios. So the first one, which is, let's say you decide to connect them in series. Then we test and see, will we get the same answer as the equivalent capacitance? If we happen to get the same answer as the equivalent capacitance, we can say that, or in that case, they are being connected in series. If is wrong, it means they are not connected in series. In that case, we go to the next stage. So we think about them being connected in parallel. We solve for them again for the equivalent capacitance, and then if it's also give us the answer, then we know that they are connected in parallel. So we start with what? The series connection here. So similar to what I just did. So these 3 are now connected in series. I will now go ahead and use the what? The simplified formula, which is, that will be the number of capacitance over what? N. So we have the capacitance is C. Here the number of capacitors, we have been told there are 3 of them. So here will be what? C over what? 3. So you can see that if we are looking at the fact that they are being connected in series, which is this way, you can see that will give us this equivalent capacitance. You see that it's not the same as what? It's not the same as the equivalent capacitance we have. So this one is wrong. So we now look at the situation whereby the capacitors are connected in what? In parallel. So let's say you connect them in parallel this way, right? I've been connected, and this is C, C, C. So here again, the equivalent capacitance will just be what? The number of capacitance times what? The capacitance. So that will be what? We are dealing with 3 capacitors, so that will be 3C. You can see that this one too is giving us the wrong answer. So that means that we can now say maybe they are being mixed up, right? Maybe they are connected in series. Two of them are connected in series and then in parallel with another one, or two are in parallel and then what, in series with one of what, the capacitors. So we can go to the next kind of connection. So let's say, for example, we say like maybe let's say two of them are connected let's say two of them are connected in parallel and then in series with what, with one of the capacitors. So this way, so you can see that the two here, they are in then. So let's try this and see if we get the same answer. So by doing this, we see that we get C here, another C, another C. So the first one here for this part, because here they are connected in what, parallel, and using the what, the equivalent capacitance, simplify one, that would just be what, 2 what C, right? So meaning the capacitor now, which is 2C here, will now be in what, in series with what, this one, right? So this is now 2C. You can see it's in series with this. So if these are in series, but now you can see now that this is 2C, that will be the capacitance for this one, and this one is C. So the capacitance are now different, and we are dealing with two of them, right? So we can now use, you have to now use this formula. The equivalent capacitance here will be equals to 1 over C1 plus 1 over C2, right? This one. Then when you simplify this, you realize that the equivalent capacitance will be equals to the product over their sum. So I'm going to get C1 here is what, 2C. So 2C times C here, all over the sum, which is 2C plus C. So if you simplify this, you can see that this part here will give us 2C squared, then 2C plus C will be what, 3C, and this C will cancel, so we end up getting this answer to be 2 over 3 times C. So you can see that we are gotten the connection, which is that two of the resistors are connected in parallel and in series with one of them. So we look at the possible answer. So you see that the first part here, all three capacitors are in series. We did that was wrong. B, all capacitors in parallel, we did that was wrong. Then C, two capacitors in parallel and one in series with what, with the parallel connection, which is C. So the answer here is C, right? So we don't have to look at the question D, which is two capacitors in series and the third capacitor in parallel across a combination. Now we go to question 50. So we have here question 50. I've not even been writing the question number here. Question 50 here. A capacitor in a circuit became hot and ultimately exploded due to wrong connection. What type of capacitor could it be? So looking at the type of capacitors, that is, you have to be careful when it comes to the connection, especially polarity, right? Is the electrolytic capacitors. Why? Because the electrolytic capacitors, what we tend to do is that we tend to combine or add some material like aluminium. We can add some conducting material to them. So as a result, because of that, they can easily become conductors. So if you switch the polarity, that can cause the capacitor to explode, right? And you can see here, so the answer here is going to be B rather, right? The electrolytic capacitor, right? Now we go to question 51. 51 here. This is done. When a 4 volts EMF is applied to or is applied across a 1 farad capacitor, it will store energy of, okay, so this one is talking about the energy stored in a capacitor. So in the formula is going to be equals to half the capacitance times what? The voltage square. So you can see from the now you just need to replace the values. The capacitance here is given as 1 farad, so that is times 1 here, and the voltage here is given as 4 volts, so that will be times 4 here, but remember it's voltage square, so square of that, so this is going to be 16 over 2, which is going to be 8 joules. So we get 8 joules, so the answer here will be D. Now question 52. If a 6 microfarad capacitor is charged to 200 volts, the charge in coulombs will be, here we are given the charge, we are given the capacitance, and we are asked to find the what? So no, we are given the voltage rather, and we are asked to find the charge. So we are given the capacitance, voltage, and we have to calculate for the charge. So it's the same formula I wrote earlier, which is charge is equals to capacitance times voltage. So we are giving capacitance to be equals to 6, right? Okay, let me go to 6 here. 6 microfarad, 6 times 10 to the power minus 6 times the voltage, which is 200. So when we do this, this will actually give us, this will be 2 times 10 to the power 2, right? 10 raised to the power minus 6 times 6 here. So this and this will give us 10 to the power minus 4. 6 times 2 will be what? 12. So you can see that we get 12 times 10 to the power minus 4 coulombs. But when you look at the possible answers, you can see that we have A 800 microcoulombs, B 1200 microcoulombs, C 900 coulombs, and then D 1600 microcoulombs. So it shows that this is being converted or being expressed in microcoulombs. So we have to do that as well. So if I'm having this is 10 to the power minus 4, I need to have what? Another minus 2 added to this. So what that means is I'll have my 12, then I have to move, right? This is the point. You have to move twice, right? 1, 2. So by moving this, that will be 10 to the power minus 2 times 10 to the power minus 4 here. And then I come and add my 0, so that will be 1200 times 10 to the power minus 6, which is 1200 microcoulombs. So the answer here is B. What is the value of capacitance that must be connected in parallel with 50 picofarad condenser to make an equivalent capacitance of 150 farad? So this question, we are giving the equivalent capacitance, right? So we are already giving one. So we are having 2 capacitors. Let's say one is here and another one, and we know they are being connected in parallel, right? And then the first one, let's say we don't know the what. We know one of them. Let's say the one we know is 50 microfarad. Then the other one is C, which is the one that we don't know, right? And we are being asked to find. And once they are being connected in parallel, the equivalent capacitance, right? This gives us 150 microfarad. And we know that for capacitors being connected in parallel, it's actually going, the equivalent capacitance will just be the sum, right? That means C1 plus C2. So let me indicate here to be C1, right? C1 is the one that we don't know, plus let's say 50 microfarad here, or 50 micro. Then we know the equivalent to what? 150 micro. So C1 is going to be equals to 150 minus 50. That will give us 100 microfarads. So the answer here is going to be what? C, which is 100 microfarad. Pico rather. Here is pico. Let me make this pico rather. They are being expressed in pico. So here will be P. Okay. They are being expressed in pico. Here will be pico. Here will be in pico as well. Pico. So the answer here is what? C. The value of dielectric constant for vacuum is, vacuum here we are talking about air, right? Remember, as I said earlier, the dielectric constant is the same as the relative permeability of what? Of a material. So here we are just trying to say that what is the value of the relative permittivity, rather, relative permittivity of vacuum, which is air, and the relative permittivity of vacuum is going to be what? 1. So the answer here is what? C. Okay, the answer here is C. Which of the following capacitors is marked for polarity? Again, this one is similar to the question we solved for a connection, right? Whereby the capacitor is being damaged. So here is going to be what? D. You have to pay attention to the polarity when you are trying to connect an electrolytic capacitor. Now, question 56. Conductance is analogous to, question 56 here. Conductance is analogous to, we know conductance to be what? Let's say conductance, we know conductance to be equal to the reciprocal of what? Resistance, right? Or the inverse of what? The resistance. Now, if you look at what the possible answers that we have A, which is the permeance, right? Permeance is also going to be equals to, when you look, permeance is equals to what? The reciprocal of what? Of reluctance. So let me use S to represent reluctance so that there will not be any confusion here. So let me use S, and S here means reluctance. So means reluctance, right? So you can see this is inverse of what? Or reciprocal of what? Resistance. This is reciprocal of our reluctance. So the question 56, the answer here becomes what? A, right? So it's analogous because they are all what? Dealing with what? Reciprocal of what? Of resistance. Reluctance here is the resistance when we are talking about what? A magnetic material, right? Now let's move to question preamble 1. Figure 1 shows a graph for magnetic magnetic hysteresis for a ferromagnetic material from the graph. For a ferromagnetic material from the graph, determine the following. You have to find, that means for question 57, the magnetic retentivity for the material. Here, retentivity, like I explained the last time, right? Retentivity is, we are looking at the ability of a material to maintain or keep its magnetic flux density when the magnetic field strength is 0, right? So let's say you have a material, right? A magnetic material. What we tend to happen is that, let's say you increase the what? The magnetic field strength, which is H here. Then here is your magnetic flux density, right? Which is Tesla. Once you start to increase this, so the magnetic flux density of the material also tend to increase. But you increase till what? It reach what we refer to as what? As a, let me do this, right? So it will increase till it reach the saturation point, right? Whereby upon increasing the magnetic field strength, there's no longer going to be any increment in the what? In the magnetic flux density of your material. So we refer to this as what? Meaning this will be corresponding to what? The saturation point, right? Now, once this happens, what we tend to do now, you start to reduce the distance. You are now going back. And when this one will reduce a bit, then we come to what we call what? Retentivity. So once you arrive at 0, right, your magnetic field strength is 0, then you look at what is the value of what? Your magnetic flux density. So we come here and look at 0, meaning your magnetic field strength, which is H here, is 0. So that means that you look at the corresponding magnetic flux, and you can see here is what? B here. And B here, the value, if you look well, is going to be what? Half, meaning it's in the middle, right? That means here is probably equals to 1.25 Tesla. So when you look at the possible answers, we have 90 Tesla, 1.2 Tesla, 1.5 Tesla, and then 100. So the answer here is what? 1.2 Tesla. Now, question 58. The cohesive force required to reduce the flux density in the material to 0. Right? So you can see with this here, the first part here, we are at the magnetic field strength here is 0, H here is 0, but you see that we still have some amount of magnetic flux density in the material. So you continue to reduce this, right? That's why you reduce this, and then once you are increasing the magnetic field strength in the opposite direction, you reach a point whereby now you get what? You actually get the magnetic flux density here to be 0. So at this point we have 0. Now the corresponding magnetic field strength that will give us produce the 0 for the magnetic flux density is what we refer to as the cohesive force. So here the cohesive force required to reduce the flux density in the material to 0, meaning we just come to the figure, we trace here, this is 0. Or we can even use the other one. You can see here too, the magnetic flux density here is 0. So the value of your magnetic field strength, you can see from 0 here is what? 100. So that means the answer here becomes 100. So D. Now question 59. The point of saturation is represented by, I already talked about this, right? You reach a point whereby upon increasing the magnetic field strength, is no longer going to cause any increment in the magnetic flux density, meaning you've reached the saturation point. So this is this part. So here you can see, if you look well here, when you reach here, that is what the A here is the saturation point, and there's another one on the negative side, right, on your left hand side, which is D here, which is also saturation. So I have A and then D based on the labeling. Yeah, so it's labeled D here. So the answer here becomes C, A and then D. Question 60. Transformers are the application of. So here transformers are the A, induction, B, mutual induction, C, electrostatics, and then D, mutual charges. The answer here will be what? B, which is mutual induction, or you can say mutual inductance. So if you look at the voltage induced in a coil, right? So if I have just one coil, for example, the voltage induced here, right, which is E1. Now if we were to bring another coil closer to what, to the first one, there's going to be what? Voltage is going to be also induced in this one too as well, which is E2. So you can see that this is what we term as mutual inductance, right? Meaning the two windings, right? Or the two coils will give you the mutual inductance. So you can see, if you look at this diagram here, you can see that it's similar to what? A transformer, right? Because we know a transformer has what? Primary windings. Windings here just meaning the number of turns, right? And then secondary windings, so which are what we have here, right? Two coils. So the answer here is mutual inductance. And that is end of what? Today's solutions, right? So we continue tomorrow. Bye bye.